Good day, class. I am Miss Amona Pitulan, your math teacher for today. For today's session, we will be discussing about theorems on tangents. For today's topic, we will have to recall our knowledge on the following areas. First, on tangents. Second, on proving, the types of proofs, how to prove, and the likes. And third, postulates and theorems that will be used on proving the theorems. We will be discussing three theorems involving tangents, namely radius perpendicular to tangent theorem, tangent perpendicular to radius theorem, and perpendicular to tangent passes through center theorem. So let's now start on our first theorem. We have the radius perpendicular to tangent theorem. This theorem states that if a line is tangent to a circle, the line is perpendicular to the radius drawn to the point of contact. If we have this circle C with tangent line L and radius CT, also with a point of tangency T, then we can say that tangent L is perpendicular with radius CT at point T. Now our task is to prove this theorem. Why does this theorem say like this? Or how did they come up with this theorem? That is the question we should answer. With the figure on the screen, given line L is tangent to circle C at point T, we have to prove that radius CT is perpendicular to line L at T. We have to prove this theorem using the proof by contradiction. It is a proof that starts with a false premise but concludes with a true conclusion because along the process we contradicted something from our false premise. So our first premise, we have to contradict our conclusion, and that is we have to assume that line L is not perpendicular to radius CT. We have here the figure. For our second premise, so if line L is not perpendicular to radius CT, then there must be some other segment, let's call it segment CD, which must be perpendicular to our tangent L. Also, there is a point R on L such that dt is equal to dr. So we can say that angle CTD is congruent to angle CTR because perpendicular lines form right angles and all right angles are congruent. Since segment CD is congruent to segment CD, then we can say that triangle CTD is congruent to triangle CTR, and that is by side angle side postulate. And so going further, by CP-CTC or congruent parts of congruent triangles are congruent, segment CT is congruent to segment CR, which means R and T are both on circle C by the definition of a circle. So this is impossible because it contradicts the given fact that line L is tangent to circle C at T because there must only be one point of tangency in one given circle. So the assumption that line T is not perpendicular to segment CT must be false, and this leads to our conclusion that segment CT is perpendicular to line L. So let's move on to our second theorem. We have the tangent perpendicular to radius theorem. So this theorem states that if a line is perpendicular to a radius of a circle at a point of intersection, then the line is a tangent to the circle at that point. Given our figure here, we have circle C with radius CT and tangent line L. With this theorem, we can say that tangent L is perpendicular to circle C at point T. Same as the previous theorem, we have to prove or come up with reasons why this theorem states this or that. So, with the figure on the screen, given radius CT is perpendicular to tangent L at point T, we have to prove that line L is tangent to circle C at point T. This time, we will be using another kind of proof, which is the two-column proof. So it is a kind of proof which is in the form of two columns. The first column is for the statements, and the second column is for the reasons. So we have to follow a logical order in order for us to arrive in our conclusion. First statement, we have line L is perpendicular to radius CT at point T, and that is of course our given. For our second statement, we can say that CT is a radius, and that is by the definition of a radius. So a radius, by the way, is a segment from a fixed point of the circle to the center of the circle. For our third statement, we have angle CTD and angle CTL are right angles, and that is by definition of perpendicularity, which states that two intersecting lines form a right angle. So for fourth statement, we can say that angle CTD is equal to angle CTL, which is equal also to 90 degrees, and that is by definition of right angles. So right angles are angles whose measures are 90 degrees. And for our fifth or last statement, we can say that our conclusion, then line L is tangent to circle C at point T. That is by radius perpendicular to tangent theorem, which is the previous theorem that we have discussed. So class, let's go further to our third theorem. We have the perpendicular to tangent passes through center theorem. This theorem states that if a line is perpendicular to a tangent to a circle at the point of contact, the line passes through the center of the circle. So if we have here circle O with center point O, and we have a diameter line AC and a tangent line DB, then if line AC is perpendicular to tangent DB, of course, we can say that line AC passes through the center point O of circle O. So again and again, our task here is to prove the theorems. So with the figure on the screen given, line AC is perpendicular to line DB at point C of circle O, we have to prove that line AC passes through point O. Again, we will still use the two-column proof. So our first column is for the statements and second column is for the reasons. So our first statement, we shall always start with our given, which is line AC is perpendicular to line DB at point C. For our second statement, we can say that The line DB is a tangent to circle C at point C, and that is by definition of tangent lines. So let us recall, tangent lines are lines that intersect at exactly one point on the circle. For a third statement, we have to draw line OC, and that is by line postulate. Line postulate states that 2 points make a line. For a fourth statement, we can say from our previous statement that line OC is a radius, and that is by definition of a radius. So let us recall, a radius is a segment from a fixed point of the circle to the center of the circle. Next statement should be OC is a perpendicular line to tangent line DB. So that is by radius perpendicular to tangent theorem, which is the previous theorem that we have discussed. For our next statement, we have line AC is a line on circle O, and that is by definition of a chord. So a chord is a segment from two fixed points of the circle. For a seventh statement, we have AO is a radius. So that is by definition of a radius. Again, a radius is a segment from a fixed point of the circle to the center of the circle. For our eighth statement, we can say that AC is equal to AO plus OC, and that is by definition of betweenness. This states that if B is between A and C, then AB plus BC equals AC. For our ninth statement, we can say that AC is a diameter. So why is that? Because it is by definition of a diameter, which states that a diameter is twice the radius. So since AO and OC are both radius, so we can say that twice the radius is the diameter. For our 10th and last statement, or our conclusion, therefore we can say that line AC passes through point O, and that is by definition of diameter. So again, a diameter is a chord that passes through the center of the circle. So class, this ends our discussion for today. I hope that you have learned something, and let me leave you with a quote. Learning is like a circle. It never ends. Thank you for watching, and this has been Miss Amona Pitula.